In this section, we'll look at transformations of functions. So this is section 1.3, transformations of functions. So there are three types of transformations that we'll consider. The first one are shifts, and these can be up and down or left to right. The second kind that we can describe is scaling, and this can either be in the form of a stretch or a shrink, and we can do both of these in either the horizontal or vertical directions. And then the last one are reflections, either about the x-axis or y-axis. Okay, so we'll start with sliding transformations, so moving things either left or right or up or down. So sliding, and we'll start with the vertical case first. So the first thing we need is just some sort of graph to work with. So for both examples, we'll just draw a simple graph, and I'll use, say, the straight line that goes through the origin. So this is the line y equals x. So we'll use this and modify it in various ways. Okay, so if we want to move this up or down, it's very simple. So our original function here is just the function x. So to shift up, use y equals x plus c for c positive. And to shift down, do the same thing, but c will be negative. So all that's doing is, for a given point, if you add c, and that's what the y-coordinate is going to be, it moves it up by the appropriate amount c. And if you instead subtract something, or add a negative, same thing, then you're going to be going down. Okay. So for example, let's say that we have y equals x plus 2. It'll be the exact same line as the red one, except it'll be shifted up by a couple units. So let's say that 2 is right there, approximately, and then our new line is going to be shifted up. So notice here that in the case that we're working with a straight line, both of my lines have the same slope, so they should be parallel when I draw them. The only difference is that the blue one is shifted up by a few units. Okay, so the vertical case is very, very straightforward. If you want to go up, you add. If you want to go down, you subtract. Now the horizontal cases are more annoying because things work backwards from how you would expect them to. Alright, so let's go ahead and draw here our same simple linear graph. So this is again the line y equals x. Okay, and so our function here, oops, I want the pencil. Alright, so our function here, f of x, is x. Okay, so that's what we'll start with, and that gives us the red line. Okay, so let's just experiment with what would happen if we worked with a new function and we did something like x minus 2. Okay. So now from the above situation, we know that what that does is, or one way that we could look at what it does is it moves everything down by 2 units. Okay. So let's go ahead and take that as given and go ahead and draw it. What would it look like if it is moved down by 2 units? Okay, so if we think about this minus 2 as being a vertical shift, then it moves it down by 2 units. So let's just kind of forget that for a moment. How else could we describe the relationship between this green line and the red line? Well, it also looks like the green line has been moved to the right 2 units from the red line. So you can either think of it as having gone down 2 units or to the right 2 units. And this is where the annoying thing happens, because we had a minus there. And if we think about what going to the right should look like, our gut tells us that it should be adding, but in fact it's actually subtracting. Okay, so the moral of the story here, horizontal stuff is generally backwards. So we would think that minus 2 should shift it to the left by 2 units, but in the horizontal direction it actually shifts it to the right by 2 units. Okay, so we'll look at another example real quick of the horizontal shift. Okay, so let's look at one more example of the horizontal shift. So this time let's choose a graph which is a little bit more interesting. And the graph that I'm going to choose to start with is just a very simple parabola y equals x squared. Okay, so the function that we're going to be working with is the function that gave us x squared. F of x is x squared. Alright, and I'm going to define a new function, g of x, which what I'm going to do is define it to be f of x minus 2. Okay? So now, how do we write this out algebraically? What this says to do is replace x with x minus 2. The x then gets squared, so we'll have to use a set of parentheses. So the function here, the new one, is x minus 2 whole thing squared. Okay. So from the last example, it looked like this minus 2 moved us to the right, not to the left, as we might expect. So let's just make sure that it does. So one way that we can kind of think of why it should move to the right instead of the left is, let's go back to the original function. If I let y equals 0, okay, so 0 equals x squared, then what value of x makes that happen? It's this one right here, right at the origin. Okay. If I do the same thing for the new curve, 0 equals x minus 2 squared, so let's just put that over here. 0 equals x minus 2 squared, then the only way this happens is if x equals 2. So this point here on the new graph, that vertex should be 2 units to the right, even though the subtraction here might make us think that it goes to the left. Okay, and if we were to do the same sort of thing for every point on the red parabola, we'd probably get the idea that all they do is also shift 2 units to the right. Okay? So subtracting inside, and what I mean by inside is that you've subtracted here before you have applied the function, gets us horizontal shifts, and subtraction goes to the right instead of the left. Now if we had added, so for example, let's say that we say h of x equals f of x plus 2, then this would be x plus 2 squared. That is going to move not to the right, but to the left. And we would say have the vertex there at that point, and then get our parabola like so. Okay, so again, moral of the story, horizontal things are backwards of what you'd expect. Okay, so the next thing that we need to talk about is scaling. And scaling is going to work in much the same way that shifting does. So again, we'll start with the vertical case. So vertical scaling. And let's just keep picking on our y equals x squared example. So we've got, say, a set of coordinate axes here, and we'll go ahead and draw in our y equals x squared parabola, something like that. Okay, so let's just keep our original function, f of x is x squared. Okay, now let's just sort of ask, what would happen if I did something like f of x, or g of x is 2x squared? Okay. Well, if I choose a point on the graph, like say for example this red dot, the vertex, what this is saying to do is to take the old y-coordinate and multiply it by the 2. Okay? So what would the new y-coordinate be that has x-coordinate 0? Twice 0 is 0. So the new graph, and let's actually make a new set of coordinate axes for it. Oops, I want black for that. The new set of coordinate axes here, we should have the new point also right there. Okay, but the other points are going to be more interesting. So let's say we also chose on the parabola the point here with x coordinate 2, and its y coordinate is of course 4 because 2 squared is 4. On the new graph, the point that has x coordinate 2 should have y coordinate 8, which it could be somewhere up there. Okay? And similarly, let's say that we pick the point 1, 1. On the new graph, that's going to be up at 2. Okay, so what we get is a parabola that's been stretched upwards. So you can just imagine grabbing both ends of this, pulling up, and if it was made out of rubber or something, then you would get a taller parabola. Okay. Now, this example for parabolas is interesting because we could also think about this transformation as taking the red parabola and squishing it in the horizontal direction in order to get the blue one. So you can sometimes think about these things in multiple ways, and that brings us to the case of horizontal scaling. So we'll do that over here. Okay, so again, we'll just work with our example, f of x equals x squared. And then I'm going to choose a new function, and I'm going to pick this one. Now, why I picked square root of 2 will become clear in just a second, but I just sort of picked it at random. Okay, so what should multiplying the x-coordinate by the square root of 2 do? Now, one just sort of side note, just so that we have an idea. The square root of 2 is approximately 1.414. It's not exactly that, but close enough. So I'm multiplying in here by a number which is bigger than 1. Okay, so our gut would tell us multiplying by a number bigger than 1 should stretch it by that amount. But again, what was the moral of the story for horizontal stuff? Everything in the horizontal direction is backwards what you'd think. So multiplying by square root of 2, or about 1.414, is actually going to shrink in the horizontal direction, the graph. Okay, so this squashes in the x direction by, in this case, a factor of the square root of 2. Okay, now I picked the square root of 2 because, and you may have already thought to do this, let's write what is f of square root of 2x. Well, f of x was x squared, so this new function is square root of 2x squared. X squared is just x squared, and the square root of 2 squared is 2. So this is what I meant by we could also think of sometimes vertical scaling as being the same as horizontal scaling, just of a different kind. So this is sort of lucky that this works out, mostly because we were considering a parabola. You can't always do this. But hopefully this is enough of an example that you get the idea. Okay, so we'll look at one more example in a minute. So the last example we'll look at is actually very easy. It's just the case of reflections. So let's draw a graph of some sort here. Now we've been picking on our friend y equals x squared, and I'm actually going to move on from him and we'll use a different example. We'll use the example of y equals x cubed. Okay, and the reason I want to do this is so that we actually get some difference when we do some reflection. Okay, so there are two ways that we could reflect this. We could reflect it about the y-axis, so moving it in the horizontal direction, or we could do it about the x-axis, sort of in a vertical direction. Okay, so let's look at both cases. So again, we'll always start here with the function x cubed. Okay, so a horizontal reflection. This is about the y-axis, because that's where our mirror is going to be. It looks like this. All we have to do is replace, so we don't want f anymore, we want a new function. Replace x with minus x. Okay? And everything in the horizontal direction you do before you apply the function. So that's why I put negative x inside the function, and then f gets applied to it. So the graph of this case would be reflecting this guy over here, and this guy would move over there. So we get the blue version like that. Now we could also reflect it in the vertical direction, so vertical reflection, and this would be about the x-axis. That's where we'll put the mirror this time. Okay, and so we'll do this one in, say, a green color, but the function that we'll use here would be g of x is, and now here's where it differs from the other one, minus f of x. Okay, so the vertical stuff always happens after the function's been applied. The horizontal stuff always happens before the function's been applied. So that's how you tell the difference. Now, for this particular graph, it actually will look the same thing. So, or look the same way. If I take the blue guy and reflect, or excuse me, the red guy and reflect him up, then I get something which is right on top of the blue. Okay. So for this particular function, reflecting it about the x or y axis actually gets you the same thing, but that's coincidence. It doesn't always happen that way. Okay, so in class we'll look at a lot more examples of this. and we'll put several steps of these together. So for example, we could do shifts and reflections and scalings, and so we'll look at how to keep track of multiple transformations when they're all happening to one function.